So this is where we will start. We will start by looking at Theorem 1. What says Theorem 1? So in Theorem 1, we've got a chord. Make sure you also know the properties of a circle. We've got a chord and a line from center. So if O is my center, then I can have a line from the center to the chord. So we will look at what happens. Let's suppose this is AB and then OC. So maybe let me even use M. If the line from center happens to be perpendicular to the chord, this is what we are given. The original color, maroon, means what we are given. And then the green color is what's going to happen. Okay? So remember, when you're stating a theorem, you say if this, then that. So let me just change colors a little bit. So maroon will be what we are given. So I'm trying to say if this, and then the green color is what is the outcome, that. So if this, then that. That is how we state a theorem. So in this case, if we are given this right here, the way this diagram looks, if we are given a line from center that is perpendicular to the chord AB, then that line will bisect the chord. In other words, it will cut the chord into two equal halves. So the green is the outcome. So if AB is perpendicular to OM, or rather if OM, because it's OM that we are drawing, if OM is perpendicular to AB, then AM will be equal to BM, because in fact M is going to be the midpoint of AB. So you could either write it like that, or you can say then M is midpoint of AB. So that is what's going to happen. So if we've got OM happening to be perpendicular to AB, then we will form a new midpoint. The reason we use here, if we are to now use this theorem as a reason, we would say line from center perpendicular to chord, because that is what we were given. We were given a line from center that was perpendicular to chord. What it does, it bisected the chord. So as a full statement, a line from center perpendicular to chord bisects the chord. Okay, that is Theorem 1. We've got the converse of Theorem 1. I'll call this converse. So converse means reverse. So we've got a converse of Theorem 1, right? Where now I'm given the line from center, yes, and I'm also given a chord. So if I've got a chord, let's say the chord is here, and then the line from center is from there to there. Now, if the center is O, the chord is still AB, and then the line from center to chord is OM. Now, what we are given is that the chord is already bisected. If M is the midpoint of AB, so if the line from from center goes to the midpoint of AB, then, remember the then is going to be green, then the line from center to midpoint of chord will be perpendicular to the chord. So what does this mean? It means what I'm given in this case is if M is midpoint, already given to be midpoint of AB, then OM will be perpendicular to AB. How do we state this one if I'm to use this converse of theorem 1? How do we state it? We would state it by saying line from center, instead of saying perpendicular to chord, we'd say line from center to midpoint of chord. So as a full statement, this is how you would state it. You'd say line from center to the midpoint of a chord is perpendicular to the chord. Okay, that is theorem 1. We may move on now to theorem 2. I'm not going to be doing examples, especially not yet. Maybe in the next video or so. But theorem 2 will be the line, angle at center equals 2 times angle at circumference. So we must identify a center again. I will call my center O. So the theorem is straightforward. It says if I've got a center and an arc, then the angle at center will be twice that at the circumference. Let's suppose that the angle is O1, and then this is A, B, C. This one is a theorem that you must know how to prove, but we will see that when we do exercises. For now, I'm not going to prove them, I'm just summarizing the theorems. So this is theorem 2. So what this theorem entails, it says because this is the angle at center, O is already the center, we know. So it says if O is center, then O1 is going to be 2 times angle A, because we already know that A, B, and C are points on the circle or points on the circumference. So O1, the angle will be equal to 2 times A. Alright, so we are not to prove this yet, but if I'm to use this as a theorem, I'd say angle at center equals 2 times angle at circumference. Okay, so that is it. This one doesn't happen to have a converse theorem, but I could show you a few more circles. We could have a center here and then an angle at center like that, and then we would have an angle at circumference like that. So if this is O and this is A, this is O1, so still O1 will be equal to twice A. Okay, it doesn't matter what it looks like. So pay attention to an arc that subtends an angle at the center and also subtends an angle at the circumference. That is what we are looking for. we are looking at a segment or an arc that subtends an angle at the center, at the same time subtends an angle at the circumference. Another angle would be somewhere here. We are allowed to have that angle. So O1 will be equal twice this angle here. Or we could even have another angle like this. So O1 would still be equal to whatever this angle is. Okay? Just pay attention to that type of geometry. Okay? So remind yourselves of the properties of any circle, but circles also have lines we refer to as diameters. So a line that is called a diameter is a line from circumference to another point on the of a circumference, and that line passes through the center, right? So we've got theorems to do with diameters. For instance, if we've got a diameter subtending an angle at the circumference, sorry about that, if a diameter subtends an angle at the circumference, that angle that will be subtended will be a 90 degrees. So basically, if I call these A, B, C, remember we said this is theorem 3. Then what does this mean? It means if AB is a diameter, so if AB is a diameter and it happens to subtend an angle at the circumference, then that angle will be a 90 degrees. Okay, so there is a converse to this angle. You can think of the converse as saying if we've got a 90 degrees, then this must be a diameter. We may be asked to prove that a particular line is a diameter. So in order to prove a diameter, we must first find out if C is 90 degrees. If we can find another different way to prove that C is 90 degrees, then we can conclude that AB is a diameter. That is the converse. It's the reverse of theorem 3, right? So so how do we use this? How do we state it if we use it? We would say angle or angles, sometimes we say angles in semicircle. Remember, a diameter cuts a circle into two halves. One half is called a semicircle and the other half is also called a semicircle. So that is why we would say angles in a semicircle, right? So this is when we have a diameter and we want to say the angle in the semicircle is 90 degrees. But if I have a 90 degrees already and I want to say AB is a diameter, then I would have to reverse this and say converse angles in a semicircle. Make sure that you repeat that part as many times as possible until it makes sense to you. You can always rewind the video. I'm moving on to the next theorem. So we've got theorem 4, which will be the angles that will be subtended in the same segment, right? And this theorem comes directly from theorem 2, not as a corollary. You will learn a few things about corollaries, but it comes directly. We can use theorem 2 to prove this one, but we are not yet proving. We will only prove if we come across a question or an activity that requires us to prove. So what are we referring to, or what are we talking about here? We are talking about an angle that may be subtended at the circumference like this, but this arc here, in fact, let me call it, or this segment here, let me call it AB, subtends C, right? This arc that is subtending C happens again to subtend, let's say, D. Then C and D are equal to each other because they are both subtended by AB. So what does, how can I write this as a theorem? If AB subtends C and D, then C is equal to D. Similarly, you could say if CD subtends A and B, then A is equal to B, right? How do I use this, or how do I state it if I use it? We just say angles in the same segment. That is how you would use it as a reason. Okay. And then comes what we refer to as a corollary. A corollary is something that comes directly from a theorem but is not a theorem on its own. So I'm going to just call it, I'm going to call them corollaries, but there's about 2 of them. This is a wrong spelling for corollary. It's corollaries. So one of the corollaries would say, if I've got chords that are equal, 2 equal chords, let me put this one like this. These equal chords should be able to subtend equal angles at the circumference, as long as I know that the chords are equal. So, like I said, the maroon is the original, and then the green is the outcome. Let me give these vertices names A, B, C, and X, Y, Z. So if AB is equal to XY, then C will be equal to Z. Okay, because it's almost like angles in the same segment. The same segment is subtending angles in 2 different places in the circumference, but those angles are equal to each other. Similarly, here we've got two equal chords that are subtending angles in the circumference. Those angles must be equal to each other. They don't need to subtend angles in the circumference. They can also subtend angles at the center. Okay, so I'll show you an example of this. Just draw a smaller circle like that, and then 2 chords, this one and that one, and then I will choose a point to be a center. Now if I've got these 2 chords, which I will say are equal, subtending angles at the center like this, what does this mean? It means I've said the chords are equal to each other. Let's call them A, B, and then X, Y, and then this will be O because it's the center. Let's call this O1 and O2. O1 and O2 should be equal because the chords are equal. So I will just say if AB is equal to XY, then O1 equals O2. I'll just put a symbol there to show that, right? So this corollary, this whole thing, we can, if we are to use it, we would say equal chords, equal angles. That is how we would use it as a reason. It doesn't matter whether the angles are subtended at the circumference or they are subtended at the center, but equal chords will be